So let's see. We are going to look at sampling distribution of a proportion. Now, to explain what is sampling distribution again, well, up until this point, we've been talking about taking a sample, running a simulation, getting some kind of test, whatever. One is never good enough. So sampling distribution is, well, let's just take multiple samples, take the average of each of these samples, and then put them on a graph, or look at that data. And that data should more or less approximate our normal curve. So you see each of these here is a average of a different type of sample. So think, I'm not going to run my test once, I'm going to run it hundreds of thousands of times just to make sure my data represents the population. And here's how the graph usually works. The sample distribution of a proportion represents kind of a normal curve where our mean is considered P, my proportion. So if I ask you for the mean of proportion, well, you're just going to find P, your probability of success. That's it. To find the standard deviation, you take the square root of your probability of success times the probability of failure divided by n. You can also see this as P times 1 minus P, which is what Q is. And yes, here's the breakdown of that proportion. So for today, mean equals my probability of success, standard deviation equals this formula. Suppose that 42% of students play video games at least once a month. The computer programming club takes a simple random sample of 30 students from a population of 792 students at the school and finds that 40% of the students sampled play video games at least once a month. The club plans to take more samples like this. Let P hat represent the proportion of a sample of 30 students who play video games at least once a month. So notice, this is my population. This is the proportion of one of my samples. What is the mean? So what is my mean? My mean is P. What is my probability for success with my one sample? 40, which is what? Oops, gave away the answer. 0.4, very good. Let's go to the pen, there we go. Equals 0.4. And our standard deviation. So that equals the square root of P, which is 0.4. What is my Q value? 0.6. So take P and subtract 1, 0.6, all divided by 30. Very good. So when you calculate square root of 0.4 times 0.6 over 30, and you should get a standard deviation of 0.089. So I have about 40% of my students that play video games, give or take, I guess 8 or 9%. So let's have you do this example. In May 2007, the Gallup poll surveyed 1,007 USA adults by telephone. When asked about evolution, that is, the idea that human beings developed over millions of years from less advanced life forms, 43% responded that this was either definitely or probably true. Although we'll never know the true proportion of adults who believe in evolution, for this investigation, we're supposing it to be 43%. So go ahead real quick, find the mean and the standard deviation. This is the thing, economics class. This is stats. Here we go. Did you get 43% for my mean? And did you get 0.0156% for the standard deviation? Okay. Now, normal model. When does the normal model with mean P and standard deviation of that work well as a model for this sampling distribution? Some things have to line up. The individuals in the sample must be independent of each other, of your data. If your data comes from an experiment, the subjects must be randomly assigned to treatments. If it comes from a survey, your sample must be a simple random sample of the population. And of course, 10% condition. What does this mean? Well, once your sample is more than about 10% of the population, the remaining individuals are no longer really considered independent. Why? So So they have to be independent. They have to be randomly assigned or randomly selected. And it has to be under 10% of the population. Anybody think what? Why does the larger I grab from the population make it less independent? Okay, here's an example. Jocelyn, you are randomly selected, but the more people I start randomly selecting, the more likely I'm to get a relative. And then it kind of becomes unindependent. Y'all can have the same views on something, right? So that's why try to keep the condition under 10%. Also, the normal model becomes more useful for describing the sample distribution as a sample size increases. So as you see here, 10 samples, 50, 100. Notice how the more samples I have, the more it's starting to look like a normal model. So the sample size assumption, the sample size n must be large enough. How large? Depends on the value of p. The closer p is to 0 or 1, the larger n must be. And we saw this last time, the success failure condition. The sample size must be large enough to expect at least 10 successes and at least 10 failures. So here's how you can represent a sample distribution with a normal model. It must meet all of these conditions.